if we're going to measure things, let's start with the basics. And here we are looking, this is actually the old kilogram. We don't have this kilogram anymore. This was at Sandia National Laboratories, just in the laboratory. There was a few all over the world. We're not using these anymore. I actually saw one in France, the original one. It looks pretty good still because it's just a cylinder in a jar. But anyway, when we're measuring things, proper measurement has three components. So the first one is units, right? Everything has to have units because in the physical world, you can't just have a random number floating around. That only happens in a math class, okay? But if you have something, there's three somethings, right? Or there's a length of 3 meters, or there's a height of 2 meters, those sorts of things. So there have to be units. And actually, if you don't have units, that's one of the few things I'm going to be a real pain about and mark off points because it's just too important for understanding what's going on. Scientific notation is a strategy that makes very big or very small numbers pretty manageable. So we're going to talk about that later in this chapter, but it's a good way to make sure that you're not just writing a ton of zeros. And then significant figures, those give you the precision. They tell you how well you measured something, both in terms of accuracy and precision. So just to start out with, hopefully some of you have seen Arrested Development or know who Carl Weathers is. If not, this is not going to be very funny, and it's basically an inside joke that I am telling myself. And I enjoyed immensely, so that's fine. So Carl Weathers walked 7. Carl took 1,100 from you. So it's very important to know of what. Is this 7 meters, 7 miles, 7 inches? That's a very different walk. Does he need to pack water, right? $1,100, 1,100 Bs. Units are important. You don't want to pay Carl Weathers, let's say, $1,100 for acting lessons that aren't going to be very good. So the other thing to know about units is you can solve a ton of problems with just units, just unit analysis by canceling your units, without actually even understanding the equations or knowing what you're doing. So if you look at the units of the values that are given in the problem, and so if you look at the units of what the solution should be, then just by trying to cancel those things out, probably like a little over half the time, you'll just get the right answer without knowing anything about actual physics. Now, it's not ideal because in this class we want understanding, but it is a good place to start if you're stuck. So the things we care about are time, length, and mass. And here's some, random units for these things. And just as a side note, how do we convert? Also potatoes, okay? In this class, I always just say, if you don't put units down, I'm going to say that the standard default unit is potato. So, and that's pretty much never the right unit. So that means you lose a point. But anyway, these are different units. They're all sort of arbitrary, made up by people for different purposes. So we need to know how to go back and forth. We need to know how they're related. Here's the question. What do these 3 countries have in common? I'll wait. Think about it. Well, it turns out they are the only countries that have still not adopted the SI units that the rest of the world has. So we're in an interesting company with Myanmar and Liberia. But here's what SI units look like. So we first have the fundamental units, and that's basically just a unit that's all by itself, right? It doesn't depend on other units. It's the core basic unit. And then we also have secondary units. Secondary units are these ones that are made up of the fundamental units, and that's okay too. Now there are more than this, and we can learn later that this actually is something called newtons, which is kind of cool, but that's where we're at on units. Now, what can you measure easily pretty much? Because you can measure speed with like certain techniques like a radar gun, but there is a certain amount of calculation that happens in those where these measurements we're going to talk about are direct measurements. So let's say you have something like a cat. Well, what are some things you can measure about the cat? Well, you can measure height and width. You can measure the size of its paws. You can measure its nose and its ears, right? So that would be lengths. You can also measure things about how heavy the cat is. That has to do with the mass. And you can measure various types of time. Like, let's say the cat sprints across the room. You could measure how long that takes. You can measure how long the cat is alive. You can measure how often the cat blinks. There's lots of different things you can measure in terms of those. So our 3 key fundamental measurements, which are also our fundamental units, are length, mass, and time. Now, there's a history of these things, and it turns out measuring things and standardizing measuring things became very interesting, primarily for beer. So in the Magna Carta, they attempted to standardize measurements throughout the kingdom, concentrating on volumes of beer and wine. So there's a lot of kings that come into this, and I'm pretty sure if you look into the Islamic Golden Age, there's some measurement standardization there too. Wasn't as well preserved in a nice document like the Magna Carta, but it's not like Europe was the only people that wanted to see how much beer they had and if they were getting ripped off by their local bartender or brewer. So going back to other history, since we live in a place that was founded by Europeans back in 1120 AD, this king named Henry I decided the yard was just his thumb to his nose. Guess whose foot is the foot? Well, that would be Louis XIV, the Sun King. And I think he might have been exaggerating. So length has evolved slightly since then. Actually, not until 1799 did France switch to the meter instead of using Louis XIV's foot. And this is defined as 1/10,000,000th the distance from the equator to the North Pole along the the particular longitudinal line that passes through Paris. So this is a very specific thing. The other fun thing about that is the surveyors that measured that line kept getting killed because of wars and, the Arctic. So that was fun times. And it wasn't until 1983 that the meter was redefined as the distance traveled by light in a particular 1/300 million seconds. Now we have something that's much more consistent than just some random guy's foot or, even a long measurement of the earth divided up.
Length, some issues with length. Let's talk about scale. Okay, why do we have scientific notation?
Really big number?
Yeah, so we can express really big stuff and really small stuff. And what's the benefit of what's the base of scientific notation?
The base 10.
Yeah, it's base 10. So it's like logarithmic, okay? So not quite logarithmic. It's by a factor of 10. So everything as you go up by exponent, it's a factor of 10. Okay, not logarithmic. But here's the size of the universe in meters, okay? And do you think we measured this with a meter stick? So the size of fun history fact about the meter. The way that it was defined previous so I don't remember when they made it based on like this laser measurement of light. But before that, the way that we determined what the meter is it was like 1/100,000th of the distance from the North Pole to the equator. And that was actually measured by surveyors who went from, a lot of them died. And I think it was like during the French Revolution. So it was like French people going from the North Pole all the way down to the equator, like measuring, and then they divided that by like, I don't know, like 100,000, and they're like, that's a meter. So this new measurement system is much less dangerous. As far as I know, it hasn't killed anybody. Yes, Miguel?
Didn't the mathematician figure out the length of the circumference of the Earth with a stick and shadow?
Probably. And then he probably died in a duel the next day. There's a surprising number of mathematicians who died in duels. Whatever that tells you about mathematicians, I'm not sure. So, anyway, distance from the Earth to the Sun. So, this size of the universe, 10 to the 26th. Okay? And that is, the order of magnitude is 10 to the 26th. I'm going to use the term order of magnitude a lot. what do I mean when I say order of magnitude? 10 to the what? Okay, so if I ask you, what is the order of magnitude of a cat in meters? Yeah, somewhere between 10 to the negative 1 and 10 to the 0, right? A cat is not a meter long, but it's not quite 10 to the negative 1, right? So it's somewhere in between there. So that's the order of magnitude, 10 to the negative 1 to 10 to the 0. Okay, you put a range on it in the 10 to the whatever. Okay, so that's what we mean when we say order of magnitude. So size of the universe, 10 to the 26th. Earth to sun distance, about 10 to the 11th. Okay, and this is in meters. Radius of the Earth, about 10 to the 8th. No, 6th. 10 to the 6th. Okay? How about a soccer field? 10 to the 2, right? Soccer field is about 10 to the 2. That's the order of magnitude of a soccer field. It's 1.2 times 10 to the 2. What is that? 120 meters. Okay, end to end.
10 people.
What?
It's 10 people.
Yeah. How about a cat? It's about 10 to the negative 1, right? And you can see it's 3 times 10 to the negative 1, so it's somewhere between 10 to the negative 1 and 10 to the 0. So if you want to put upper and lower limits on it, that's a good way to do it. Because in physics, what we always start with is estimating. Okay, so you want to know the order of magnitude of the answer or the values you're supposed to expect. How about a fly? No, let's say on the order of a millimeter. So a millimeter is 10 to the what? 10 to the negative 3. So fly is on the order of 10 to the negative 3, 10 to the negative 2. Okay? How about a virus? You don't have to know this one. Negative 7-ish. A virus, I think this is just like a standard registry. I don't remember what it is. I should write down where I get these images. That would be good. So yeah, virus, super small. Anybody know the wavelength of light? Visible light.
It's 450 to 700 nanometers.
Okay, so 10 to the what?
9.
Well, if it's 400 times 10 to the negative 9.
Oh,
10 to the negative 7. Okay, so if it was 400 times 10 to the negative 9, that would be 4 times 10 to the negative 7. So, wavelength of light, about the same size as really tiny microorganisms. So, and this we won't talk about in this class, but just as a future preview, when you look at something through a microscope, what's the limit of how small the thing is you can see? Let's say it's a light microscope.
Yeah.
The wavelength of light. Okay, it's about, you can see things about on the order of the wavelength of light. So do you think this image was taken with a standard microscope? No, yeah, this is an electron microscope image. So turns out, this is a big preview, electrons are also waves, and they have a much smaller wavelength, and so you can image smaller things using electrons. Although a lot of the times, the thing about electrons is they're like waves that hurt a lot more. So a lot of things imaged with electron microscopes, if you use like the standard kind, it like this virus is smashed now. You got a really good picture. Okay. Yeah. So you have to like destroy things to see them. Okay. Let's talk about mass. So historically, mass has been, well, up until last year actually, mass what looked like this. It was just a little, it's like palladium or something. A cylinder in a jar that you would take out and be like, this is a kilogram, okay? Which, it was the last thing that we did that way, because a meter used to actually be a stick that somebody had, and there were like 3 different locations on Earth where you could go see the meter, okay? The problem with this is what they found was this kilogram kept losing weight. Like, I don't know if it went on some sort of diet or whatever. But it was getting smaller. They didn't know where the mass was going. It was this totally weird thing. So that's not how we do it anymore. Yeah, so it used to be, this is old. I should change the tense. But the kilogram used to be defined as platinum iridium. As platinum, this platinum iridium cylinder, but that was problematic. And the cylinder was kept in France, and there was a guy that there was one in the U.S. too, and one in Asia. So they have 3 places that you could look at there, and they would get them together and compare them. They had a special way of measuring them. It was very cute. But now we use Planck's constant. Okay, so we had standardized meters with the speed of light. Now we've standardized mass with Planck's constant. And honestly, you kind of need to take a whole nother class to really understand how we do that. But the general idea is we use an electromagnet. Everybody know what an electromagnet is? It's pretty simple. You just wrap wire around, usually a metal like iron, and then you run a current through it. And it turns out you can build a scale that's very, 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 very precise. And it's called a kibble balance, which is not named after dog food. It's named after a guy named Brian Kibble, which is just a hilarious name. And obviously you have to be Dr. Kibble if you have a name like Kibble. So basically you can put anything over here, you can measure it with great precision over here, and it has to do with Planck's constant. You can measure to an accuracy of 0.000001, so 10 to the negative 6. Yeah, 10 to the negative 6. So, 1.000000 kilograms. You're pretty sure it's a kilogram. Okay? So, no longer do we have just a cylinder that is this is the kilogram. I mean, it is nostalgic and they still have it, but the standard is now based on a kibble balance, which is something that you can build if you have at least $3,000. Okay. Time. We're not going to go into the history of time because nobody really cared that much about time until clocks, and even then you had the Industrial Revolution. There's a whole thing. But the second is that number times the period of vibration of radiation from a cesium atom. So when you hear atomic clock, what is the atom? Cesium. Okay, so, and this is, cesium's a metal. It's in that column. It's an alkaline metal. What's special about the alkali metals? They're the ones under hydrogen.
Hyperreactive.
Hyperreactive? Why?
Because they tend to want to lose an electron in order to reach noble gas configuration.
Yeah, noble gases, super stable. Alkali metals, not so much. Table salt, right, is sodium chloride. If you have just sodium, and and if you put it in water, it's a really fun explosion. And the farther you go down, the more exciting the explosion gets. So, but the fun thing about the alkali metals is they all kind of look like hydrogen. Okay, now we're not going to get into this that much in this class, but atomic structure is pretty cool. There's a nucleus, and then there's electrons. And when things get bigger, we kind of smash the inside electrons in with the nucleus. And we're that's all one big thing. And then the electrons do crazy things on the outside. Well, if you only have one valence electron, one electron that's free to move, okay, one electron that's way out there away from the other electrons, hydrogen is the simplest thing because it's positive charge, negative charge. And the negative charge forms these cool clouds that are very geometric and pretty. But actually, they're just a visualization because we don't know where the fuck where the electron is, okay? But it forms these nice configurations. All of the stuff below hydrogen behaves sort of like hydrogen. So in terms of how physicists think about atoms, it's fun because hydrogen's the easiest one to know what it does. We can calculate it on paper, the different structures that hydrogen takes. And so anything that looks like hydrogen is fun. So if you do atomic physics, which is what I used to do, then you really like alkali metals, and you have a lot of little jars of them. They're called vapor cells. A vapor cell is basically a glass bulb with a little tail, and you put a tiny, tiny bit of the metal in the tail, and it evaporates into the cell, and then you shoot lasers at it. Summary. Okay. Before 1960, which wasn't that long ago, the standard of time was defined in terms of the mean solar day. So the average amount of time of a day, okay, from the year, guess the year? There's no rhyme or reason to it, so any guess is good. 1900. So someone just measured all the days in 1900. They found the average length of a day. And that's the mean solar day. So that is a solar day is defined as successive appearances of the sun. Okay? And, I mean, somebody had to figure out how to define these things. And then the second was defined as divide by 24, divide by 60, divide by 60. That was how we used to define the second. Now, cesium. Okay? And, these things don't line up perfectly because there's some migration. Like, we think of, like, the day and the orbit around the sun and all that stuff as being pretty static, but it's actually not. Like, even the spin of the Earth has changed over time. Like, if you go back, like, when most life on Earth was, like, squishy things in the sea, it turns out the Earth spun a lot faster. They didn't care because they were underwater, but if you, like, drill down into ancient coral fossils, you can see, because there is a periodic nature of coral, right? Coral is there's that structure, but there's a bunch of little animals that breathe in there. And guess what? They're more active when there's sun, okay? Because there's more food, and they're more dormant when it's dark. So you can actually see how many days are in the year, and you can tell the year because the seasons change, and so the little, like, sizes of the layers change, okay? Because basically you're probably just counting their poop, because that falls to the bottom of the ocean, right? And it turns into rocks, and then we can look at it millions of years later. But the orbit around the sun has been fairly constant, but the spin of the Earth has changed, and the moon actually moves. So in your lifetime, that's not a big deal. Like, the day from today to tomorrow is not going to change that much. But if you lived, like, even 10,000 years, it's not that standard. So standardizing the second is pretty exciting. I can tell you're excited. I'm pretty excited. So, yeah, that's how we used to do it. Now it's cesium. Unfortunately, before that was pretty easy to understand, right? Average day, divide by 24, divide by 60, divide by 60. Now you have to take some atomic physics class just to know how clocks work. Okay, so some scale of time. Age of the universe, approximate 10 to the 17 seconds. Okay, if you really want to know how we know that, you can take a cosmology class. Okay, age of the Earth, slightly smaller, 10 to the 17. Okay, average age of a college student, about 10 to the 8 seconds. Okay, some of you are older, some of you are younger, but on the order of 10 to the 8. 1 year, about 10 to the 7th. Okay. See, and you can see how many times this is this. About 20, right? So you're all on average about 20, according to this. 1 day, that's 10 to the 4th. 1 class period, I don't think this class is that one, but 10 to the 3rd. Time interval between normal heartbeats, 10 to the -1. Period of audible sound waves, that's 10 to the -3. Radio waves, 10 to the -6. Vibration of an atom in a solid, 10 to the -13. Visible light waves, period, about 10 to the -15. Duration of a nuclear collision, 10 to the -22. And time interval for light to cross a proton, which is it's kind of a distance almost, but whatever.